Hello, my name is Mason Cipollini with my partners Mackenna and Mayra Mendoza. This is the Faraday lab for OPTI 471A.
Faraday's rotation is when polarized light rotates as it passes through the material that is inside a magnetic field. The magnetic field twists the light by an angle that depends on the material's Verdant constant, the strength of the magnetic field, and the length of the sample. This effect is important because it is used in optical isolators and many photonic devices. It also helps us measure the magnetic fields and understand how light interacts with matter. For this lab, we sent a 543 nanometer helium neon laser through a solenoid with either a glass rod or a water cell placed in the middle. We changed the current to change the magnetic field, and we measured how much of the polarization rotated. We used two methods: the maximum extinction method, where we rotated the analyzer to find the maximum light, and the fixed intensity method, where we bring the signal back to half the maximum. We also tested a non-reciprocal setup to show the basic idea of an optical isolator. For the glass rod, the rotation increased in a straight line with current, just like theory predicts. We measured Verdant constants at about 87 to 218 degrees per Tesla meters, depending on the method. For water, the rotation was much smaller, which is expected because water has a weak magneto-optic response. The non-reciprocal test also worked. The reflected power increased when the current went up, showing the isolator effect. Overall, the results followed the expected trends very well.
In this part of the lab, we measured the stress optic coefficient, which describes how much birefringence a polymer develops when mechanical stress is applied. As shown on the slide, the induced index change is proportional to the applied stress, and the constant Q tells us how strongly the material's refractive index responds. This is useful in stress analysis in understanding how plastics behave under load. Experimentally, we set the Heaney laser polarization at 45 degrees to the stress axis and aligned the analyzer for extinction at 0 force. Then we recorded transmitted power as we increased force, first in large steps to find the first maximum, and then in small steps in the low stress region. Using the formulas on the slide, we converted the transmission data into birefringence and plotted birefringence versus stress. The small interval data was nearly linear, and from the slope we extracted a stress optic coefficient on the order of 10 to the minus 12 square meters per Newton, which matches typical polymer values.
What we liked most about this lab was that in the stress optic coefficient experiments, we were able to clearly see the sinusoidal patterns that we were expecting. What we liked least about this lab was how feather-like of adjustments you had to be with the stress optic coefficient, as the smallest adjustments would cause a drastic change in the birefringence.